This lecture, we'll be looking at another way to transform parent functions. And we'll look at how to stretch and shrink functions. And once we understand that, we'll try combining all of our transformations in one example. So for stretching and shrinking, we call these non-rigid transformations, since it will fundamentally change the shape of the graph. Instead of just sort of sliding it around and shifting it through space, or rotating it with a reflection, we're going to be actually taking the graph and stretching it tight like a rubber band, or shrinking it down and letting it flatten out. So to get an idea of how this works, let's start by comparing the graph of f of x is equal to x squared to g of x, which is equal to 2x squared. So we'll start, and let's begin by graphing our squaring function here. By now we should be familiar with this table. Goes for 1, 0, 1, 4. And in red, let's complete the table of g of x is equal to 2x squared. And this will be 2 times 4, which is 8. 2 times 1, which is 2. 2 times 0, which is still 0. 2 times 1, which is 2. And 2 times 4, which again is 8. So we've taken all of our y values, and we've stretched them up by a factor of 2. All the numbers have been doubled. And when we compare the graphs, we can see the stretch take place before our very eyes. So let's start by drawing down some Cartesian planes. And we'll mark off our favorite numbers here. And on the right-hand side, we'll have to mark up to 8. So let's try to do that without getting it too crowded. 5, 6, 7, 8. All right. Here's 8. Here's 2. And now in blue, we'll graph f of x is equal to x squared, which we should be quite familiar with by now. And we'll have our u-shaped function here. And now let's graph our new stretched function, which was 0, 0, negative 1, 2, 1, 2, negative 2, 8, and 2, 8. And we can see, if maybe we try again here, that this function's been stretched very, very tight. It's sort of like we've taken the two sides and we've just pulled them up, so it's much tighter now. And again, we can see that the shape has fundamentally changed. Sort of the lax U-shape is now a very tight U-shape. And so we say this is a non-rigid transformation. And we have general rules for stretching and shrinking that are similar to our rules for shifting points in the plane. So let's say we have some function f of x and a real number c. We say we have a vertical stretch when c is greater than 1. And this means the function is now pulled very tight together. It's stretched up high. On the other hand, we say we have a vertical shrink when c is between 0 and 1. And what happens is we sort of squish the function down and we let it shrink and shrink, sort of like squeezing a rubber band together. We can also define these for a horizontal stretch with the same rules and a horizontal shrink where they're inside the parentheses. But in general, we only care about vertical stretches and shrinks, since normally we can take a horizontal stretch and do the math, and actually just compute it as a vertical stretch or a vertical shrink, and that makes it easier for us to sort of compute. So for example, if we had the function f of x is equal to x squared, and we tried to have a vertical stretch by 3 on the inside here, well, if we changed our function and we put the 3x inside the parentheses, then we're allowed to square each of these individually. So parentheses 3x squared should become 9 times x squared. And so this horizontal stretch by a factor of 3 is the same thing as having a vertical stretch by a factor of 9. So by just considering vertical stretches and shrinks, we can simplify our problems and focus on how the y values are changing instead of worrying about how the x values change. And this is as far as it goes for stretching and shrinking. There's nothing more complicated we can do. So now, let's try combining all of our rules in one example. Now, if you're given a function and you want to know how to graph it and it has a lot of transformations, then I would recommend doing them in the following order. Start by looking to see if you have any horizontal shifts and mark those off on your graph. Then do any y-axis reflections, followed by your x-axis reflections. Then do vertical shifts, and once you've taken care of all of that, then you can start stretching and shrinking your graph by whatever k you're multiplied by. So how does this factor out? Well, to see how this works, let's try it with an example here. And we'll mark off all the different transformations we have, and then we'll put it on the graph to see what it should look like. So let's start by listing them all out. Do we have a horizontal shift? Yes. Since we have a -1 inside the parentheses, then we have a horizontal shift 1 unit to the right. Remember that the horizontal shifts work the opposite of what we want. So even though it's subtracting 1, it's actually making it more positive. Okay. Do we have any x-axis reflections? And the answer is no, since we don't have a negative on the x value. So none. But we do have a x-axis reflection, since we have this negative sign outside the parentheses. So we do have an x-axis reflection. Then we have a vertical shift 2 units up. The ones outside the parentheses behave nicely. So if it says +2, then we move it +2. And we have no stretching or shrinking, since we have no constant multiplied on the outside of our function. So now we'll take these and we'll do them in this order, and we'll come up with the correct transformation of our original parent function, f of x is equal to x squared. And we'll do this in a couple steps here. So let's start by marking down our parent function. Okay. And then we'll start shifting our points. So in red, we'll shift each of these 5 points, 1 to the right. So 0 becomes 1. -1 moves to 0. And our -2 value moves over to -1. And likewise in the positive direction. And now we have our first transformation. Next, in blue, we'll do an x-axis reflection. So remember, we think of the x-axis as a mirror, and all the points flip over it, changing the y values. It's outside the parentheses, so the y values are what get changed. Our first point at 1, 0 isn't going to move at all since it's touching the x-axis. And all the y values for the other points just flip to become negative. So now we have 0, negative 1, negative 1, negative 4, 1, 0 we've already taken care of, 2, 1 becomes 2, negative 1, and 3, 4 becomes 3, negative 4. Alright, now we've done the x-axis reflection, and the last thing we need to do is shift all of these points 2 units up. So in green, we'll shift all of our blue points 2 units up. And we'll see we actually have some points in common with the red transformation. And now we've done them all, so we can fill in the shape. And if we did this correctly, then this is the graph of g of x. So again, we can check to see that we did this correctly by plugging in some x values to our function and making sure we have the correct y values. So why don't we start by plugging in x is equal to 1, and we'll see here's x, here's g of x. If x is 1, and this is negative 1 minus 1 squared plus 2, which is negative 0 squared plus 2. Negative 0 squared is still 0. And 0 plus 2 is 2. So when x is equal to 1, y should be 2. And there we have it. Let's do one more point here. Why don't we plug in x equals 0? So this is negative 0 minus 1 squared plus 2, which is negative 1 squared plus 2. Negative 1 squared is 1, but this negative on the outside turns it back into a negative 1. And negative 1 plus 2 is 1. And so when x is equal to 0, y should be 1, which it is. We've checked these 2 points and they check out, so there's a good chance that we've done this correctly. And it turns out we did. Now we don't just have equations when we look at these. Sometimes they give us a parent function and they want us to write down the altered transformation just by looking at a set of examples or a set of, well, descriptions for how we're actually altering the function. And there's a couple things that we need to be wary of when we're trying to solve problems this way. The first one is that if we're given a set of transformations that we're supposed to perform, we should always do it in the order that they're listed. If we try to do all of the horizontals and then all of the verticals, we'll end up having the wrong function because the reflections can really change how we're doing it. So always take them one at a time and do them in the order they're listed. The other thing that can mess things up is when we do y-axis and x-axis reflections. So anytime it tells you to do an x-axis reflection, remember that everything inside the parentheses is multiplied by negative 1. This isn't just the x that gets affected. This is also the vertical shifts in the plane. They also need to be flipped, as well as the horizontal shifts. And so we have the same rule down here. If we ever see an x-axis reflection, then we need to multiply both the parent function and the vertical shifts by negative 1. We don't just add a negative to the outside. We need to flip the vertical shifts as well. So let's see if we can do this with an example here. And our goal will be to take the function f of x is equal to x squared, shift it 2 to the right, 1 up, and then reflect over the y-axis. So this should be the word over here. Okay, well let's do it one at a time. So we start off with x squared, and the first thing we should do is add in a horizontal shift 2 to the right. So right is positive, meaning we need to subtract 2 to the inside of the parentheses to have our shift. Okay. 1 marked off. Now we'll take this function and shift it 1 up. Oop, made a mistake there. So we have f of x minus 2. We add 1 to it to have our vertical shift of 1 up. And this becomes parentheses x minus 2 squared plus 1. And then we'll reflect this over the y-axis, which means we're changing the x values. So everything inside the parentheses gets multiplied by negative 1. So this is negative x minus 2 plus 1, which is negative x minus 2 squared plus 1. And the negative gets distributed to both terms here. So this becomes negative x plus 2 squared plus 1. So our shift 2 to the right, once we do a y-axis reflection, in the mirror should be a shift 2 to the left, and we see that by our minus 2 becoming a plus 2. And now we've completed all three. So our function h of x should be equal to negative x plus 2 squared plus 1. Okay, so let's do one more example where we look at a function and work out the transformation. So we'll look at one more example, and we'll try to graph this, and we'll follow our 5 rules here. So we'll write out the steps, and then we'll move our points to create the function. So we start off by asking, are there any horizontal shifts? And the answer is yes. We have a shift 1 unit right. When we subtract it, it makes it more positive. Now we ask, do we have any y-axis reflections? And the answer is no. We have a positive x, no negative signs right here, so no y-axis reflection. Now do we have any x-axis reflections? The answer is yes. We have a negative right out here, so we do have an x-axis reflection. Now, do we have any vertical shifts? And the answer is yes. We shift 2 units up. And again, we have no stretching and shrinking. So now, let's graph the function of this, following our steps listed. And we should know our points for the square root function. They are 0, 0, 1, 1, and then 4, 2. And then we make this gradually sloping hill here. And we'll move these points according to our rules, one at a time. So first we'll shift all of these points 1 to the right. Okay. Then we have an x-axis reflection. So now all of our y values get flipped to be negative. So 1, 0 stays the same. 2, 1 becomes 2, negative 1. And 1, 2, 3, 4, 5. 5, 2 becomes 5, negative 2. And we've done our x-axis reflection. And again, we finish by shifting it 2 units up. So the blue points all move up by 2. And now we can draw the graphene. And this is a weird looking one. It's the same shape, but notice we have this hard stop at the point 1, 2. And the reason why that is remember we can't take square roots of negative numbers. So we need the inside to always be greater than or equal to 0. Or in other words, we need x minus 1 to be greater than or equal to 0. Which is the same thing as saying that x has to be greater than or equal to 1. Okay, so our domain is 1 to infinity. And our range, since we have this negative up top, will get flipped to be negative. And our smallest point should happen when x is equal to 1. So if we plug that in, then x is equal to 1, and this is the negative square root of 1 minus 1, which is 0. So 0 plus 2 is 2. And so that's our point on the range where we start, and then everything gets smaller. So the range is 2 to negative infinity. And we see the domain and range has changed pretty drastically from our original square root function. So this will be the end of this lecture. And we'll see some more examples in class probably of different ways to transform and combining all of these in one.